last questions that we didn't get to from Friday, or I think it's just one question, because we're talking about mechanisms for reactions, how we could write these reactions and come up with sort of elementary reactions that add up to produce the entire reaction and also match whatever the experimental rate law is. And actually, I think what I've done in the past is we'll have from an experiment, we'll have the overall reaction, right? So we'll have the balanced chemical equation. We can determine all that experimentally. And then we'll have the rate law as determined experimentally. And those things are gold. We treat those as the truth. And when you write a reaction mechanism, it has to match those two things. And the reaction mechanism is mostly theoretical. So when we're looking at something like, actually, let's go to the easier one first. If the first step is the slow step, then our rate law will actually reflect that in having only reactants from the overall reaction. It doesn't have to have all of them, but only reactants from the overall reaction will be involved. So like here, again, the thing that's gold, the thing that is our standard that we're trying to match is that we've got the overall reaction and we've got the experimentally determined rate law. And now we are trying to make the connections between those two really to come up with the multi-step process that might occur to explain why the rate law doesn't depend on carbon monoxide. And that's the case when our first step is slow. When our first step is fast, things get a little bit more complicated. All right, so imagine this is the test. I give you this question and I say, prove that this mechanism is valid. How do we prove that the mechanism is valid? Has to add up to the overall equation. And the rate law that comes out of really our slow step has to be equal to the rate law determined experimentally. So our overall thing, that's where I had things crossed out, right? We can't have, or the intermediates will cancel out, things like this will cancel out. The nitrogens are on this, or hydrogens are on the same side, nitrogens on the opposite side. So we could prove that those add up to the overall equation. That's good. We also need to show, so I guess we should say, elementary reactions or steps to overall. Check that off, that looks good. But now how do we show that the rate law of this reaction is equal to the overall rate or the experimentally determined rate? What is the thing that's true for elementary steps that we can't do for overall reactions? We can determine the rate law of an elementary step just from the elementary step. Why? What's different? Yeah. Yeah, the overall reaction might have intermediate steps, as shown by these elementary steps. The elementary steps, each of them represents the exact collisions that are taking place to make the products or intermediates. And so when we write out an elementary step, since we're writing a step that describes a specific interaction that's happening, we can look at that and say, is it, as we learned, be unimolecular, bimolecular, or termolecular? Although termolecular, not very common. But because on this reaction, we're saying that, for a slow step at least, hydrogen reacts with dinitrogen dioxide. What I'm saying in this elementary step is those two things have to collide. And since the reaction, well, let me ask you, what does the rate of this elementary step depend on, concentration-wise? Does changing the concentration of hydrogen affect this elementary step? Yeah? No? Yeah? Yes. Right? If I'm saying I need hydrogen in here to react, again, for an elementary step, we're talking about a specific collision. If I have less hydrogen, that's less reactions. That's going to make it slower. What about dinitrogen dioxide? Does its concentration affect the reaction? Yeah. I need both. And it's going to be first order for both, because if I double the amount of hydrogen present, I double the number of hydrogens able to collide, and so the rate should also double. So we can write out a rate law. Usually denote these with subscripts. It'll be K2, and then it'll be the concentration of H2 times the concentration of N2O2. And I know this is kind of already what we did on Friday, but I want you to know why and not just a series of steps that'll help you to figure out what. Okay, so we're trying to match this rate law to the overall rate law. Clearly that doesn't match. And the problem is that dinitrogen dioxide is an intermediate. And I think just from a practical perspective, we can't measure the concentration of an intermediate. We can't change the concentration of an intermediate being added. I mean, we might be able to inject dinitrogen dioxide directly rather than letting it happen because of this first step. But just based on this, that doesn't match our overall rate. But what we can do, and this is the case for any, or at least I'll say most, reactions where the second step is the slow step, we can use the fact that this first fast reaction is fast. Right? This is like the traffic jam with the 50 lanes of that Chinese freeway that runs into 20 lanes through a toll gate. This is the toll gate, this reaction. So all of our dinitrogen, or all nitrogen monoxide, sets off to commute to work, and then it gets stuck in a traffic jam. It turns into dinitrogen dioxide, and then it just waits. So what happens then is, because that's all backed up, this, while it's waiting around, will reach equilibrium. And at equilibrium, even though we haven't talked about it yet, the rate of the forward reaction is equal to the rate of the reverse reaction. And because, again, we can write rate laws for elementary steps, I can write out a rate law for the forward and the reverse reactions. So for the forward, we can call that rate 1 will equal K1 times NO2 squared. All right, so that defines the rate of that forward first step in the elementary reaction. And that's going to be equal to the reverse reaction, which is just N2O2. And the K is -1, bless you, because it's for the reverse of the first reaction. We could even write out here, rate equals -1. So again, trying to prove that this reaction mechanism is valid. Said elementary steps add up to the overall, that looked good. Now we're trying to prove the rate. And really all we're trying to do here is like a system of equations where we're trying to redefine the concentration of N2O2 in terms of one of our reactants from the overall reaction, nitrogen monoxide. And really what we're doing when we take this rate, we set it equal to this rate. Right? The amount of dinitrogen dioxide depends on the equilibrium between these two things, whose rates will depend on the concentrations and K. And so I can actually take this and I can figure out the concentration of dinitrogen dioxide as it depends on nitrogen monoxide. So we can take this whole thing and rearrange it to be and right, and divide both sides by K minus 1 times NO squared equals, not K. Now really, if I could find what K1 and K negative 1 was, I could plug in some concentration of nitrogen monoxide and figure out what the equilibrium concentration of dinitrogen dioxide would be, which feeds into this rate law, which would tell me the rate law for the overall step. And then I can just plug in this for this. And we get the rate actually for the overall would be K2, K1 over K minus 1 times H2 times NO squared. Which matches the overall. Yes, even though I wrote out the K's here, right? K2 times K1, those are the rates for both forward reactions, and divided by, or slowed down by, you could almost think of, by the reverse rate for the first reaction. So the overall K is just all of the forward K's multiplied, divided by the reverse K's multiplied. If you didn't pick up already, going over that twice, I think this is important. Hint, hint. It's like the perfect tie-in between this chapter and the next chapter, but we're not there yet. Any questions about this?
Hint, hint, this will be on the test.
Yes. Hint, hint. Just to be perfectly clear. Yeah. And again, it's not about memorizing how to do this problem and then matching that to whatever problem is on the test. It's being able to do any of this type of problem and explain it, understand it. And okay. Yeah.
For the overall rate, the K constant, is it important to write it in terms of the other things that K1, K2, inverse K?
You mean like that I had it here as, I would probably rewrite this if I wanted to match to the overall, I would rewrite it as just K. But that overall K is equal to the product of the, intermediate Ks. But in terms of like points on a test, if you wrote the overall and gave me K2 times K1 divided by K negative 1, I'd be okay with that. Any other questions? I did assign this type of problem on Friday. So they're on Alex. All right, so let's move on and let's talk about, oh, right, there was another one to do. That's okay, this will be good practice. Catalysts don't take very long. There's not that much to actually know. So this is exactly the type of problem that I was just describing. Show that this proposed mechanism is consistent with the experimentally observed rate law. And I will say, in terms of writing out a mechanism, I wouldn't expect you to be able to write out something where the first step is fast. That's really hard. When the first step is slow, I might ask you to write out a mechanism, because then you know that the first step is determining the rate. That gives you the rate law. It's just coming up with the overall reaction. So what do we need to do to show that this is experimentally sound? Yeah. So yeah, one of the things we need to do is determine that the rate of our slow step at least adds up to, maybe with a little bit of algebra, the overall rate, or the experimentally observed rate. The other thing we could do is just first say that, oh, do these add up to my overall reaction? And the overall reaction, very simple, is O3, or 2O3, 2 ozones, turn into 3 oxygens. So down here, you get rid of all the single oxygens because they're on opposite sides. And then this is going to be 2O3 and 3O2. So that's good. Those match. But yeah, now this next part is the harder part, arguably. So I can write out a rate law for my slow step. And we're going to call this rate 2 is equal to K2 times O3 times monooxygen but that doesn't match because it's got an intermediate in it. Can't have an intermediate in our rate law. So we have to redefine the concentration of that intermediate in terms of one of our reactants or our products. And so for our fast step that comes before that, we can write out rates. We can write out a rate law. K1 is O3, which is equal to K -1 times O2 times oxygen. Why can I set those equal to each other? We're at equilibrium, so the rates are the same. If we're not at equilibrium, the rates are not the same, can't set them equal to each other. How do we know it's at equilibrium? 2 ways. It's the initial fast reaction, so it gets bottlenecked by the slow reaction that comes after. There's another way that we can tell that it's at equilibrium. The arrows, equilibrium arrows. So the equilibrium arrow here also tells us this is at equilibrium. Okay, so now we just rearrange this in terms of our intermediate. All right, so we're trying to solve for this concentration of oxygen so that we can replace it. And then I can substitute that in. oh, I guess I could rewrite this as, just to like really match, mathematically the same, but to the -1. So what does it mean that oxygen, O2, which is one of our products, is part of the rate law? What does it mean that we have oxygen O2, which is one of the products, not one of the reactants? That's part of my rate law, though. What does it mean that a product is part of the rate law? If it's part of the rate law, does it affect the rate? Yeah. And it's in the denominator, as written here, right? The -1 means it's in the denominator. So if I increase the concentration of oxygen, what does that do to the rate? It decreases it. So really, as this reaction goes, it's going to produce oxygen, or the more oxygen that's present, the slower this reaction will go. So you can have a product that is part of the overall rate law. It's not super common, but it is possible. You just can't have intermediates. Okay, catalysts. Catalysts. So this is another way that we can affect the way or the rate of reactions. What are all the ways? What are some other ways that we can affect the rate of a reaction? Temperature, that's the easy one. Got to go for that low-hanging fruit while it's there. What else? Surface area. Not one that we've really talked about, but yes. Huh? Mixing? All right, yeah, we can go through everything from concentrations, usually. I'll say those are the big ones. In terms of things, part of the equations that affect reaction rate, temperature, and concentration. And surface area, it's basically changing the concentration, right? If you increase the concentration or you increase the surface area, that's more molecules that can react at the surface. Mixing is kind of, in a way, also increasing the concentration, because if you've got two concentrated zones, they only react at the barrier. If you mix them together, now they're reacting throughout. Catalysts are another way that we can change the rate of a reaction. Oh yeah, concentration and temperature. Should read my own slides. The catalyst, though, increases the reaction rate. It's not another reactant because it's not consumed. So it doesn't get used up. But it provides another route for the reaction to happen that lowers activation energy. So really the big three are temp, concentration, and, oh, I can just use EA, activation energy, that determine how fast a reaction goes. So our activation energy can be reduced or really changed. So again, with our decomposition of ozone, which happens up in the upper atmosphere, the regular path takes this blue route, has this higher activation energy, higher energy transition state. So happens really slowly. The thing about a catalyst is I'm not actually changing the transition state here because I'm introducing something new. And so I'm creating a new path and really a new mechanism by which things can react that has lower activation energy. So generally, ozone is a good thing. And actually, this isn't even really that much of a problem anymore, as long as we keep doing the things that we've been doing to prevent it. Chlorine is what catalyzes the decomposition of ozone in the upper atmosphere. So it creates this new pathway with a lower activation energy, so it reacts faster. And in our reaction here, or proposed mechanism, really, we have chlorine reacting with the ozone to become hypochlorite. Well, not hypochlorite because it's not an ion. Chlorine monoxide and oxygen. And then another chlorine monoxide can react with oxygen, or a single oxygen, to create O2. And then our catalyst is restored. And so it's not even really part of the reaction, or at least wouldn't be written in as part of the overall reaction, because our overall reaction is still O3 to O2. Or actually, wait, does the ratio change? Oh, I see here. It was O3 plus O. So because we're introducing another path, it's lower in activation energy, the reaction goes a lot faster. You also have catalysts in your car, if it's gas, which use rhodium or palladium or platinum, which this is why people steal catalytic converters, because they've got these really expensive metals in them. Not a ton, but they've got enough. And these work by turning other pollutants into non-pollutants. So nitrogen monoxide and carbon monoxide, both pretty bad, as an understatement, turns it into nitrogen gas and CO2. Or it can take uncombusted fuel and really finish that combustion to turn it into CO2 and water. And chlorine and catalytic converters are two different types of catalysts. So homogeneous catalysts are ones that exist in the same state. Heterogeneous catalysts are ones that exist in different states. So the catalyst in your car is a solid, but it's a solid that has a very, very high surface area. Lots of places where the air or exhaust can make contact with the catalyst. You don't just put a single sheet of the catalyst in the car. Would not work very well. So how many guys of you know about or knew about the ozone hole? Good. Okay, most. All right, cool. Did you know we mostly fixed that? Like it came back? The way we stopped it actually was related to my research, because I used methyl bromide as a fumigant, which is a great fumigant, super good at killing not just insects, but also other like microbes and other pathogens. So one of the problems, so we phased out methyl bromide and a lot of other things because they have halogens, chlorine, bromine, not fluorine, although to a certain extent fluorine. So CFCs are chlorofluorocarbons. They're great for refrigerants. They're great for killing insects and other pathogens. The problem is that they get used and then they leak eventually. Maybe not today, maybe not tomorrow, but eventually all the things that we use these in will leak, and it will get into the environment. And as it's being produced, it'll leak into the environment. And the problem is that these compounds, even though chlorine or bromine or iodine or even fluorine will probably never make it by themselves into the upper atmosphere, when you attach them to a carbon, that makes them more stable. And so instead of reacting with something at ground level, they get carried eventually up into the upper atmosphere where we need ozone. We don't want ozone down here, but we want it up there. So we fixed the hole in the ozone layer by just banning these substances. Just like stop using them, which means we had to find other things, which is why like Old people will complain about how refrigerants aren't as good as they used to be, like the car's AC isn't as cold. It's okay, we can live with it. The thing I was going to say about methyl bromide, though, it is a great fumigant because it kills insects and it kills microbes. When it got phased out, they started using other fumigants, which was good. I'm not going to argue that it was bad, but it did introduce unexpected problems because they didn't realize that the methyl bromide they were using was also killing things like E. coli or other foodborne illness-causing pathogens. So they killed the insects and made sure that they weren't being transported. Good. But there was an increase in other microbe-based outbreaks for a while. And then they figured out, oh, we need to clean things better, which is more expensive than treating with methyl bromide. So these compounds, though, get transferred into the upper atmosphere. And then in places where it's warmer, they tend to spread out faster. But when they get to areas that are colder, they tend to get trapped in those colder areas. And so that's why, particularly over the poles, or Australia especially, they had worse, the hole in the ozone layer was a lot worse. Because these compounds that would catalyze the destruction of ozone would build up there, concentrate there. And so like clouds would hold on to these and catalyze all of these reactions. And eventually the chlorine does leave the atmosphere, but that's why it took a very long time. We banned these things and then had to wait for them to sort of be purged from the upper atmosphere. Another reaction, if you take OChem, you'll see this reaction. Hydrogen double bonds, you could use this even in unsaturated fats, which are the bad fats. Wait, no, unsaturated fats are the good fats. Saturated fats are the bad fats. Unsaturated fats have double bonds in them, called unsaturation in organic chemistry. Can be catalyzed, the destruction of those can be catalyzed with platinum, palladium, or nickel. Almost always transition metals. Normally these reactions, double bonds you can't get rid of them very quickly or very easily, but you add a catalyst in and it creates a new pathway by which you can remove double bonds or react double bonds to make them single bonds. So for catalytic hydrogenation, like that's what hydrogenated vegetable oil is. They've taken it and they've added hydrogen to all of the double bonds. So our catalyst in this case really is represented as this sort of sheet of purple atoms. In reality, we're looking at this at a tiny, tiny molecular scale. So that sheet of purple atoms is really just like a teeny tiny fleck because you add this stuff in usually as a powder because high surface area. Higher surface area means more reactions. So the hydrogen and the stuff with double bonds, ethylene in this case, can both be adsorbed, which means that they get added to the surface. Same way that human hair adsorbs water, doesn't absorb it, it sticks to the surface. And then on the surface of this, the hydrogen atoms actually get split. Or the hydrogen molecules, right, H2, get split up into H. And just by breaking that bond, which is a decently stable bond, that already lowers the activation energy for this hydrogen to react with the ethylene. And so as they're dancing around on the surface, they'll eventually run into it. Once it gets added to the ethylene, then the ethylene leaves. It's the double bond that allows it to stick to the surface. And for the most part, that's catalytic, doesn't damage the surface. The surface just acts as a mediator, the meeting place, if you will, for the hydrogens and the ethylene. Biological catalysts are enzymes, and enzymes are really cool. They do some ridiculous things that we can't do with regular chemistry yet. So for biological catalysts, our enzymes will have a reactant molecule, which is the substrate, binds to some active site in the catalyst, and then greatly lowers the activation energy of the reaction. And there are a lot of different ways that this can happen. So we talked about the orientation factor right? Things have to be oriented correctly to react. Enzymes can catalyze things by forcing the orientation factor of two molecules. So one binds to the enzyme, the other binds to the enzyme, and they can only bind in the correct orientation. And once they're bound, the enzyme can just basically smash them together and cause them to react. So we take that factor of, oh, well, they need to hit in just this right way and with an amount of energy, and we basically remove that. So if it binds with the catalyst, it will react. So in general, you could say, right, our enzyme or substrate, it creates a new fast first step. And then the products can leave. One of my favorite examples of this is actually the digestion of sugar. Sugar, sucrose specifically, hard to react and hard to rip apart at room temperature or body temperature. Not just room temperature, body temperature. But sugar catalyzes the reaction by weakening the bond between the glucose and the fructose rings. So sucrose comes in, it binds, and then the enzyme basically puts it in a chokehold and then rips it apart and puts a ton of strain on the bond between the two molecules, lowering the activation energy, causing it to break. It's just, in a world where so many things are chemical, and maybe we'll have a greater appreciation for this after organic chemistry, where we're relying on the relative energies of different species to collide, and especially when they have to collide in certain angles, certain things, the idea that you could just take a molecule and mechanically pull it apart is wild. And that's what this enzyme does. So enzymes are great because they give control over reactions when they occur and how they occur and the rates at which they occur, but they're extremely specific. So like that enzyme for sucrose only works for sucrose. If you're lactose intolerant, your body lacks the enzyme to break down lactose. So if you can't break down the lactose, then other things break it down and turn it into hydrogen, mostly, and methane, which can cause gastric distress. So you're just lacking that specific enzyme. Your sucrose enzyme can't react with lactose. Many substances that are toxic inhibit specific enzymes. So you block a certain pathway, that stops a particular enzyme, that causes lots of problems. Nope, I was thinking cytochrome C oxidase. Actually, I guess it's relevant. That's an enzyme. One of the fumigants that I used specifically blocked cytochrome C oxidase, which is a necessary enzyme in the electron transport chain for cells. And most things don't have an alternative to that. If you block that, you completely block cellular respiration and cells die. Versus in another fumigant that I used, it blocked glycolysis. So it blocks a different enzyme. Lots of animals, plants have alternative enzymes or alternative reaction pathways. So blocking glycolysis is not like the end-all be-all. So what do I want you to know about catalysts? How do catalysts reduce the activation energy? It could be one way. I'm thinking more general. Yeah. So catalysts add a new pathway with a lower activation energy. They're not directly changing the activation energy of the existing pathway. They create a new pathway. That's pretty much it for catalysts. No math with catalysts. At least not yet. I don't know if there's going to be, I don't think there is, but not for this chapter. Not for this chapter. Oh, cool, just on time.